Welcome to our educational video on enzymology. By the end of this video, you will be able to learn kinetics of enzymes and factors affecting enzyme activity. Kinetics of enzymes depends upon two factors, velocity or rate of reaction and factors affecting enzyme activity. Velocity or rate of reaction is determined by the rate of change of the substrate to the product over a specific time interval. Here a reversible reaction is given below. Your R1 describes the rate of forward reaction. R2 describes the rate of backward reaction. A velocity or rate of reaction is directly proportional to concentration of the reacting molecules. At equilibrium, rate of forward reaction is equal to rate of backward reaction. Therefore, concentration of substrates is equal to concentration of products. Here K represents constant. Then K1 by K2 is equal to concentration of products by concentration of substrates. The K1 by K2 is set as equilibrium constant. Therefore, equilibrium constant is equal to concentration of products by concentration of substrates. Here, equilibrium constant is the ratio of reaction rate constants of forward and backward reactions. If equilibrium constant is equal to 1, then rate of forward and backward reactions are equal. If equilibrium constant is more than 1, then rate of forward reaction is more favored. If equilibrium constant is less than 1, then rate of backward reaction is more favored. Now let's learn factors affecting enzyme activity. The first factor is enzyme concentration. The graph of velocity of the reaction to enzyme concentration shows straight line. So, velocity or rate of reaction is directly proportional to concentration of the enzyme. Substrate concentration. The graph between velocity or rate of reaction and substrate concentration explains the effect of substrate concentration on enzyme activity. This graph is explained in three phases. The initial interphase. At very low substrate concentrations, the curve starts as an upward-sloping straight line. Here, the reaction rate is directly proportional to substrate concentration. There are plenty of free enzyme active sites, so adding more substrate linearly increases how fast the reaction goes. Curve transition phase. As substrate concentration increases, the slope of the curve starts to decrease. The enzyme's active sites are getting busier. Not every added substrate molecule finds free site as easily, so the rate still increases, but less dramatically. The plateau phase. At high substrate concentrations, the curve flattens into a horizontal line. This is the maximum reaction rate. All enzyme active sites are occupied, so adding more substrate doesn't speed things up, it just waits in line. Likely's constant. The enzyme and substrate combine with each other to form an unstable enzyme-substrate complex for the formation of product. The K1, K2, and K3 represents velocity constants for the respective reactions as indicated by the arrows. The equation from these constants is made into K2 plus K3 by K1 is equal to Michaelis constant, where K is constant and M is Michaelis. The equation obtained after suitable calculation is shown below. When concentration of substrate is made equal to Michaelis constant, then V is equal to 1 by 2 V max. The Michaelis-Menten constant is defined as the substrate concentration to produce half maximum velocity in an enzyme catalyzed reaction. It indicates that half of the enzyme molecules are bound with the substrate molecules at that particular substrate concentration. The Michaelis-Menten is independent of enzyme concentration. It is inversely proportional to affinity of the enzyme towards its substrate. The lesser the numerical value of Michaelis constant, the affinity of the enzyme for the substrate is more. Lineweaver-Burke plot or double reciprocal plot. It is used when high substrate concentrations are impractical. It plots 1 by V against 1 by substrate concentration to determine Michaelis constant. This graph is made from reciprocal Michaelis-Menten equation. Product concentration. As product builds up, it can slow the reaction by shifting equilibrium, competitively inhibiting the enzyme or triggering feedback inhibition. The effective temperature on enzyme activity. Enzyme reaction velocity increases with temperature, reaching maximum at the optimum temperature. The temperature coefficient measures the rate of catalysis increase with 10 degrees Celsius rise, typically doubling the reaction rate. Enzyme activity decreases with temperatures above 50 degrees Celsius due to denaturation. Most human enzymes function optimally at 37 degrees Celsius, while some bacteria thrive in hot springs with enzymes optimized near 100 degrees Celsius. The graph of velocity of reaction to temperature shows bell-shaped curve at which the rate of reaction is slow at low temps, optimal in the middle, and zero after denaturation. The effective pH on enzyme activity. Enzymes have an optimal pH where their active sites, charge, and shape are ideal for substrate binding and catalysis. The pH determines the charge on the amino acid residues at the active site, influencing substrate binding and catalytic activity. The optimum pH varies depending on temperature, substrate concentration, and ions. Enzymes typically have an optimum pH between 6 and 8. The graph of velocity of reaction to pH shows bell-shaped curve in which the rate of reaction is slow at low and high pH and optimal in the middle. Enzyme activators. Enzymes require inorganic metallic cations and occasionally anions for optimal activity. These metals function as activators, combining with substrates, forming complexes, participating in reactions, and altering enzyme structure. There are two categories of enzymes requiring metals for their activity: metalloenzymes and metal-activated enzymes. These activators are already discussed briefly in coenzymes video and art channel. Enzyme inhibitors. Inhibitors are substances that reduce the rate of an enzyme-catalyzed reaction either by blocking the active site or altering the enzyme structure. They're critical in regulating metabolism, designing drugs, and understanding enzyme kinetics. These inhibitors will be discussed briefly separately after this video on our channel. If you found this video helpful, please like, share, and subscribe.